Today we're going to talk about finding extrema on an interval. Before we go about finding them, we're going to define what they are first. So there's two kinds of extrema that you'll find on a graph, minima and maxima. So mathematically, minima are defined as function values such that this value is less than all other function values for all x in the interval I. So what this means is, in this interval I, this is the lowest point on the graph. Maxima are defined exactly the opposite. They're function values such that this value is the greatest of all function values in the interval I. So a maxima is just the highest point on a graph. This leads us to the extreme value theorem. This says if f is continuous on a closed interval I from a to b, then the function has both a minimum and a maximum in the interval. Basically what this says is every continuous graph has both a highest point and a lowest point, which is pretty obvious. Let's say I have this graph and we're going to analyze it from a to b. We can see that this function is continuous, so that means the extreme value theorem applies, meaning there is a highest point and a lowest point on the graph. The highest point would be here, and the lowest point would be here. Now look what happens when I draw the tangent line to the graph here and tangent line to the graph here. See that they're both flat or they have a slope of 0. If they have a slope of 0, that means the derivative of the graph at this point equals 0, and we're going to use that fact to our advantage to find extrema. This is what brings us to critical values. These represent potential locations of extrema. And like I said before, we're going to use the fact that the tangent lines to the graph are flat at extrema. The formal definition of a critical value is if the derivative at c equals 0 or the derivative at c is undefined, then c is a critical value of the function. So we've gone over why this might be an indicator of a critical value, because if you draw the tangent line to a smooth graph at its extrema, then it's flat. But we add this derivative is undefined part to account for cases like this. For the spike graph, the derivative at the top here doesn't exist, but we can still clearly see it's an extrema. And if we just had this condition, we would have missed it. So that's why the definition of a critical value includes derivative is 0 and derivative is undefined, and you always have to check for both. It's also important to know that while all extrema are critical values, not all critical values represent extrema. And this mainly has to do with the case where the derivative is undefined. We're going to consider the graph right here. At this point, the tangent line to the graph is vertical, so the derivative is undefined. But we see that it's not a minimum or a maximum of the function. So this still is a critical value of the function, but it doesn't represent an extrema. Now, using everything we've just gone over, this is how you find extrema on a closed interval a to b. First, we want to start by finding the critical values of the function. And remember, we do that by differentiating it and then setting it equal to 0 and solving for x, or considering when it's undefined. Then we're going to go ahead and evaluate f of x at each critical value. And then after that, since we're in a closed interval, we have to consider the endpoints too. So we're going to evaluate f of x at the endpoints a and b. Finally, we're going to compare all their values. The smallest number you got by evaluating f of x is your minimum, and the largest number you got doing that is your maximum. As an example, we're going to find the maximum and minimum of f of x equals 6 sine of 1/2 x on the interval negative pi to pi. So first, I'm going to start by differentiating my function. And we see by the chain rule, it's 3 cosine of 1/2 x. Now we need to consider when the derivative is 0 or undefined. And when I do this, I like to make this chart so I can organize my information. When we check to see when this is undefined, we see that it's actually never undefined because cosine is always defined for all x, so this does not apply. And when we want to check when the derivative is equal to 0, we can just set our derivative equal to 0 and solve for x. Dividing by 3 on both sides, we see cosine of 1/2 x equals 0. That 1/2 x equals the inverse cosine of 0. This is basically asking the cosine of what angle gives 0. If you know your unit circle, you know that that's pi over 2 and 3 pi over 2. And because there's two possible answers, our equation splits into two equations. Here we see that x equals pi and x equals 3 pi. But if you look up here, we're only asked to find the extrema on negative pi to pi, and 3 pi is outside the interval, so we're just going to ignore the second solution. Now we have to check the values of f of pi and f of negative pi. And notice that while this is our critical value we just found, it's also the endpoint of our interval, so we don't have to check it twice. We see that f of pi is 6 and f of negative pi is negative 6. Negative 6 is the lowest value that we found, so this is our minimum. Positive 6 is the biggest value we found, so this is our maximum. And that's how you find extrema on an interval.